Hello, this is Sarah Samir, and I'm from Singapore Institute of Technology. Today, I will be discussing my work on GiNet, which focuses on integrating sequential and context-aware learning for battery capacity prediction. This is a joint work between SIT, ST Engineering, and NTU. Links for our paper and code is available on the slide deck for you to access. Moving forward, here's a quick overview of what we will discuss in today's presentation. We'll start off by defining the problem statement along with our research motivation, and then we will dive deep into the technicalities of our work, and we'll finally conclude it with some upshots and some future research directions. So, let's start with something we all interact with, which is batteries. From smartphones to electric vehicles to solar energy, everything has batteries. And we are moving forward towards a cleaner and safer version of energy, so the dependence on battery is only going to increase. But here's a problem. Batteries doesn't last forever, and their health does not always degrade as we expect. In a recent study from Stanford, they predicted that EV batteries last up to 40% longer than what is expected. It tells us that our existing models might not be able to keep up with the real world scenarios. And we need more models, more robust models that think in terms of real driving scenarios and not some mimicry lab experiments. So, to begin with, the critical part of any battery health management system is state of charge. State of charge basically tells you how much charge is left in the battery before it runs out. And to estimate it properly and accurately, it's very important because it can tell us how we can optimize battery performance and how we can prevent the batteries from overcharging or deep discharging and how we can eventually maximize the battery's life. There are methods like Kalman filters and SVR that have been used before, but they rely on battery assumptions about how a battery works and how the internal dynamics work in a battery, due to which these models struggle to perform in real world scenarios. So for our experimentations, we pick a public data set, which is Panasonic batteries. But what's good about this data set is that it has examples of different discharging temperatures and different drive portfolios, which mimic the real world scenario, and it gives us a chance to build a model that is generalizable across different profiles and different temperatures. The features that we have used in our experiment are basically only 3 features that are radially available and measurable in real time as well. These features are current, voltage, and temperature. So our motivation is to build a model that can capture the complex dependencies in the data, and this is where Transformer comes in. Transformer is well known for its ability to capture long-range dependencies in the dataset. It's because of it doesn't use any recurrent layers, which saves a lot of time and makes it more efficient, and it's best suited for complex temporal patterns. It's widely used in NLP tasks and in time series tasks, and it makes perfect sense to use this model to model the battery time series and use it as a way to estimate state of charge. But Transformer comes with a limitation as the data grows. To address this limitation of efficiency, we have used informers, which is a variant of transformers for this application. Informer is just an efficient version of transformer with 2 key benefits, which we will discuss in the subsequent slides. So, like in transformers, informers also need positional encoding to retain the sequential structure. Since it's not a convolutional-based architecture, it needs some kind of architecture within its model to understand the sequence pattern of the data set. So in addition to the conventional positional embedding that's part of Transformers architecture, we have added 2 additional embeddings to enhance the feature space, which is value embedding and temporal embedding. So the first one is value embedding that takes the raw data and convert it into high dimensional vectors using 1D convolutional layers. It basically adds more contextual information in addition to the position information. And the temporal embedding adds cyclic information to our data set, to our feature representation. It basically tells us in what time, in particular to what unit or what second, the data was captured. So it gives a more cyclical pattern of the data set. The positional embedding gives the position of the sequence, and value embedding basically gives a higher dimension of those features. So we concatenate all these embeddings to make our feature space, and then we fed this into our informer architecture, which we will discuss in the next slide. So on this slide, you can see the attention, the conventional attention expression that we use in the transformer matrix, in the transformer architecture. So that's what's happening under the hood. So after getting the concatenated input from the embedding layer, we project the input into the attention layer, and the attention is basically the crux of informer. That's what differentiated from the transformers. So the main differentiating point between the transformer and informer is the way attention scores are computed. In traditional transformer, full attention mechanisms are used where all input points attend to all input points, which form a dense n by square matrix. It's computationally very expensive when you are dealing with large data sets. So to counter that issue, Informer brings and introduces a new idea, which is prop sparse attention. It's a unique concept of focusing on only informative timestamps in the input based on its learned probability, and it computes attention score of only top k important timestamp, which significantly reduces the time computation of calculating the attention score of every other timestamp. So this is the key benefit that Informer offers over transformers. The other benefit that Informer offers is the use of knowledge distillation. Knowledge distillation is a very popular concept in model tuning and model efficiency. It's basically the idea that the knowledge is transferred from a larger model to a smaller model to make it more deployable and efficient. So in our case, distillation is basically an internal architecture feature in informers. We use distillation operation between the encoding layers to reduce the input size to half as it moves forwards while retaining the important information. So as it reduces the input size to half, it also reduces the memory usage and it makes it more deployable in real world scenarios. And this is very critical for those applications which run on embedded system inside the EVs. So based on our insights, we developed GiNet, which basically comprises of GRU layer and informer network. GiNet takes 3 battery features which are measurable in real time in real world scenarios, which is basically current, voltage, and temperature. It slices it into the window size to make it adaptable and make it adaptable to the sequential processing task. The reason for using GRU prior to Informer is that it can capture short-term dependencies in the dataset and make it more temporal aware. We can think of GRU as a lightweight choice, which basically acts as a smoothing filter. It basically smooths the short-term temporal noise. It's like a soft filter that prepares our model for deep temporal modeling. And this architecture, together with GRU and Informer, is designed for robust and effective prediction of SOC. Here is basically our experimental setup. We have kept some driving profiles and some temperature restricted to the testing dataset that is unseen in our training part. This is to mimic the real world scenario where every test case is not known to you. The table in the red basically shows all the hyperparameters that we have used to generate our results. And to evaluate our results, we have used RMSE and MAE. Basically, these are the performance matrix, the lower the better, as it says in the literature. Now, finally, what do we get from our GiNet? When we compare our model with the baseline LSTM and the standalone GRU and Informer networks, we see that GiNet consistently achieves lower errors, which is the better in our case. And more importantly, it maintains the performance under different temperatures, under different driving patterns, under different forecast horizons, and under different input lengths, which gives us a very good edge to say that this model is more robust and more generalized. And as we increase the input size and the forecast window, we can see that the conventional models like LSTM struggle to achieve good results, but our model continues to achieve good results even in different scenarios. To better understand how our architecture affects our performance, we conducted a sensitivity analysis on different numbers of encoders and decoders layers. We basically tested 3 setups, one with only 1 encoder and 1 decoder, one with 2 encoders, 2 decoders, and one with 2 encoders and one decoder. And we saw that our model kind of find a sweet spot between the encoders and decoders layers, and it performed very well on 2 encoders and 1 encoder architecture setup. So we continued with this architecture to perform all our analysis and to finalize our results. So where are we heading next? Now, there are 2 dimensions that we are interested to explore now that we have come up with a model that is robust and is able to generalize under different scenarios. But there are still some directions that we want to explore with our existing GiNet model. Firstly, we want to use physical models like ECM and electrochemical models that basically tells us how the battery operates. It tells us about the physical knowledge of the battery. We want to integrate that physical knowledge into our GiNet and together see how robust our model can perform with having a more enhanced feature space. We want to quantify our prediction confidence with uncertainty-aware forecasting. And lastly, we want to optimize our model for on-device SOC estimation. Our aspiration is to develop lightweight models that can be deployed in real time. For that, we can currently building a minimal parameter models. So yeah, that was the quick overview of my work. And if you have any questions or comments, please do share. Thank you so much for your time.